Okay, let's get ready for your midterm exam coming up this week. So your packet, make sure you're pretty comfortable with everything in the packet, and you should be fine. You should do really well. So first of all, we kind of introduce the real numbers, um, and then this was tied into every Prezi presentation. So let's review the fundamental theorem of arithmetic. The fundamental theorem of arithmetic, the definition is that every natural number greater than or equal to 2. So we're not going to include 1. So from 2 on has its own unique, and that's the big idea, its own unique fingerprint. And when we say fingerprint, we really mean prime factorization. So, for example, any natural number greater than or equal to 2. So if we look at 375, so we've done tons of these. 375, we're going to break it down and find its unique fingerprint. We're going to find its prime factor. So 375, you punch it in your calculator. You recognize because it ends in 5, we're going to divide by 5. So if we do 375 divided by 5, we get 75. Okay, now 5 is a prime number, so let's keep going on 75. 75 divided by 5, that's 25. Hold on, it's not 5 and 25, it's 5. 75 divided by 5, it's 5 and 15. So 5 is done. 15, let's break that down. That breaks down to a 5 and a 3. Okay, so the fingerprint for 375 is really equal to 5 cubed times 3 to the 1. And the order doesn't matter, which is equal to 3 to the 1 times 5 cubed. So the primes, the list of primes, the string of primes, the very first prime is 2, then 3, then 5, 7, etc. So this is a big deal. How come 1 is not considered to be a prime? And 1 is not a prime because of this word right here. Every natural number greater than or equal to 2 has to have its own unique fingerprint. And if we say 1 was a prime, 1 would throw the idea of having a unique fingerprint out the window. For example, if 1 was prime, if we let 1 be prime, then this would be the fingerprint of 375. 375 could have the fingerprint of like 1 to the 7th times 5 cubed times 3 to the 1. And that is also equal to 1 to the 3rd times 5 cubed times 3 to the 1. And 1 to the 7th and 1 to the 3rd are two totally different fingerprints, even though they both give a 375. So if I write them out, 1 times 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 5 times 5 times 5 times 3, that looks totally different than 1 times 1 times 1 times 5 times 5 times 5 times 3. It looks different because I've got a lot more 1s, but anytime I times by 1, it doesn't really change the value. So they both return a 375, but the uniqueness is totally thrown out the window. So because we have to have a unique fingerprint, we're going to say 1 is not allowed to be prime. The first prime is going to be 2. Okay, now the two categories of real numbers. Real numbers are classified either they fall in the rational group or the irrational group. So those are the two categories of real numbers. They're either rational or irrational. And here we go. So the natural numbers, this is the very first set. The natural numbers start with 1, 2, 3, 4, and they go all the way to infinity. The whole numbers include all the naturals, but they start with 0. So 0, 1, 2, 3, dot, dot, dot. The integers include all the wholes, which include all the naturals. So they go 0, 1, 2, 3, but then they introduce negatives. Negative 1, negative 2, negative 3, all the way to negative infinity. Okay, then the rationals, which include everything that we've covered so far, they include all of the fractions in between. So the 1/2, the 3/4, 1, 2, 3, dot, dot, dot. So the fractions, any fraction, so let's look at 1/2 and 3/4. Any fraction that can be written as a decimal, where we're going to be picky about the decimal. The decimal either does this, it either stops, it terminates. 3/4, we say that's 0.75, or it can go on forever, like 1/3 is 0.333 forever. So it either terminates, or it stops, or it goes forever, but it's got a pattern. So the irrationals, these are decimals that cannot be written as fractions. So they're decimals that can't be written as fractions. You can never turn it into a fraction. Can't be written as a fraction. So these are kind of weird numbers. So they're decimals that go on forever, but they have no pattern that we can pick up on. So we cannot kind of anticipate what's coming next. So 1.414213562, and it goes forever. So this one is the square root of 2. So most of your square roots are going to fall under this irrational category. So they're decimals that go on forever, but there's no pattern. They're unpredictable. They're kind of chaotic. Pi 3.141592. I mean, so if it is a decimal that cannot be turned into a fraction, it's irrational. And your calculator only shows the first 10 or 12 digits, but there are an infinite number of digits after that just cannot fit onto your calculator screen. So the real numbers are both categories. They're all these, the rationals, integers, whole numbers, naturals, and the irrational. So all rational and irrational. So those are the real numbers. Any number that exists on this number line. If that's 0, this is positive, infinity, negative, anything on here is a real number. Okay, so then we started with NRN1. So the idea of introducing rational exponents. So what's happening when you have 3 to the 4th? This is just repeated multiplication. You've got 1 times 3 times 3 times 3 times 3. So you multiply 3 by itself 4 times. And this is something that's pretty familiar. This one maybe not so much. What happens when you got a negative exponent? If you have 3 to the negative 4, you start with 1, but instead of multiplication it's division. Divide 4, not divide 4. We're dividing by this number right here. We're dividing by 3, and that's how many times we do it. So it's 1 divided by 3, divided by 3, divided by 3, divided by 3, divided by 3. So we do it 4 times. Okay, now this is brand new, introduced sophomore year. What happens when you have 3 to the 3/4? Okay, so it's positive, so it's multiplication, and it's 1 times, but anytime you have a rational exponent, what's happening is radicals. So 3/4 is going to be this. We're going to have 3. This is where that 3 comes from I'm talking about. The 3 goes there. And then if it's 3/4, you're multiplying it by a 4th root. And this is how many you got. You got 3 of them. So I got that. 4th root of 3. 4th root of 3. So this is how many I got. And this is the radical that's being introduced, and it's a 4th root. And that is the same thing as 1 times the 4th root of 3 cubed. So if I've got 3 of them written out, just like I've got like 3 times 3 times 3, so I'm repeatedly multiplying. Let's write it as an exponent instead. That is 3 cubed. Just like this is this 4th root of 3 cubed. Okay, so where we go? So the big idea is this. If you can morph, if you have a, and you're going to raise that to like the x over y. So you're introducing a rational exponent. What you're introducing is a radical. And the a goes here, the x would go here, and the y goes there. So this is a big idea. You got to know how to morph from an irrational exponent, or from a rational exponent to a radical. And you can go back and forth. So these first 3 express the following in their simplified radical form. So these are given in exponential form. So let's morph them to radical form. Okay, now this is kind of a tricky guy. So the 32, it has an exponent of 1, and the x has an exponent of 5. So 32 we can't really touch, and x to the 5 is really, I think this is a typo. I meant to do 1/5. So this exponent, man, I messed up. That's going to be okay though. We'll change it. So this exponent is just a natural number 5. It is not a fraction. So you can't really morph it to a radical form. So if you write out the long way, you just have, again, just 132. So it's like 32 times x times x times x times x times x. You got 5 of them. That is nothing special. So it kind of introduces this. If you look at it as 32x, if we try to make a fraction out of this 5, it would just be like 5 over 1. So the 32 would just be like a 1 over 1. And there is no such thing. If we go to morph it and we put like a 32, 1 to the 1, and x to the 5th to the 1, the index of 1, I mean, it kind of doesn't even exist. So things come out, it undoes groups of 1. So that one will undo that one, which will just give you a 32. And this one, well, if I got a power of 5, there's 5 ones in there, so it undoes all those. So a root of 1 does not really exist. The very first root that we want to introduce is going to be a square root. So it's going to undo squares. It's going to undo powers of 2. So undoing powers of 1 is really kind of pointless. We want to wait until they get greater than 1, so we want to undo powers of 2. So let's morph, let's change this typo. Let's do this. Let's do 32 times x to the 1/5. Okay, now let's morph that. So your 32 has an exponent of 1. So not really going to morph that to a radical, but this guy right here is what we're going to morph. If you got x to the 1/5, what that means is we're going to have x there, the 1 goes here, and the 5 goes there. There we go. And because it is an index of 5, so it's a fifth root, it's going to undo powers of 5. So anytime I got a power of 5 or more, it's going to be inversed by this fifth root. And since I only got 1x, nothing's going to happen. Okay, this guy too is a typo. It really should be 1/5. So let's look at it as 1/5. Now, the difference is this is going to both the x and to the 32. It's going to everything in the parentheses. So it's like 32 to the 1/5 times x to the 1/5. Okay, now that's different than 32 to the 1 times x to the 1/5. So here we go. If I morph this 32 to the 1/5, you can have 32 to the 1/5, and it's all times. This is 32 times x. You can do them as two separate radicals, x to the 1/5, but because they are both fifth roots, I can combine them and write them as just one. So I can write that's a fifth root, and I can go 32x there. And this is what we want you to do. Anytime that your index is the same, if they're both fifth roots, multiplication just times these radicands together. So times 32 and the x together, and just rewrite it as one radical. Okay, the next one. X to the 2/3 multiplied by x to the 1/2. So that a simpler version would be something like this. If we have multiplication happening with power, so I've got x squared and x to the 4th. Because the powers have the same base, I can add the exponents. So it's going to be x squared, x to the 2 plus 4, which is going to give you x to the 6th. And that's what we're going to do here. So anytime that we are multiplying powers with the same base, since this is an x and this is the x, they're the same base, I'm going to add the exponents. So let's go up here. Let's go x to the 2/3 plus 1/2. And this, I mean, at this point, if you're not comfortable with fraction, this is just a calculator. So just punch in 2/3 plus 1/2, hit it on your calculator, type it in, hit enter. Your calculator will simplify it for you, and you're going to get x to the 7/6. Okay, now we got a rational exponent. So anytime we got a rational exponent, that is introducing a radical. And the radical is the x goes here, the 7 goes there, and the 6 goes there. So it is the 6th root of x to the 7th. And it's not quite simplified, so we got to simplify this. Now, simplifying, I have got a 6th root, so it's going to undo any powers of 6. So if I've got the 6th root, if I got 7 x's, there is really a power of 6 in there. So I'm going to rewrite them. So I'm going to split up the 7. I'm going to do a group of 6 and a group of 1. And this 6th root is going to undo this power of 6. So what that means, if you ever have this, they undo everything and then you just have x. So this x comes to the outside And your final answer is this. You have got the 6th root. We've got an x on the outside, and it's all times. And then you got this 1 left over on the inside. And you don't need to write 1s if you don't want to. You can just leave them out. Okay, let's look at these. So same thing. These top 3, let's leave them in radical form. Okay, now if there is no index, so I got a 4th root, if there's no index, it is understood to be a square root, so it's a 2. So I've got the square root of x to the 4th to the 1/2, and you can simplify this right here. So it's a square root, so it's going to undo squares. And if I've got x to the 4th, that's like x, you got 4 of them. But that is a square, and that is a square. So it's like x squared, x squared. So this square root is going to undo that square, so x comes out, and it's going to undo that square. So you're going to have x out. So you bring both of these to the outside, and you're going to have on the outside x squared, and nothing left in. And you're raising that to the 1/2. And now this, if you ever have an exponent raised to another level, you got to multiply them. So it's x to the 2 multiplied by 1/2. And again, just punch this in on your calculator, hit 2 times 1/2, and calculator should spit out that is just x to the 1. And you don't even need to write the 1, it's just x. So that's your answer. Okay, the middle one, you got the 4th root of x squared. So now it's index of 4, so things come out in powers of 4, but I don't have enough. I only got a power at 2. So my first move, I'm going to morph this. So I'm going to transform it to its exponential form. I think my slate's running out of battery. So if we morph it, we're going to have x here. The 2 is the numerator, and the 4 is the denominator. So that is a radical morphed to an exponential. And I got to raise all that to the 1/3. Okay, now 2/4. You can simplify that, so we can go x to the 1/2 raised to the 1/3 power. And what happens here is you multiply your exponents. So you've got x to the 1/2 multiplied by 1/3. Okay, and again, that's a calculator move. Punch that in, and you should end up with x to the 1/6. Okay, but that's exponential form, and they wanted it in radical form. So this one, I kind of morphed everything into exponential form, and I'm going to morph it back. So to morph it back, I'm going to go to radical, the x goes here, the 1 goes there, the 6 goes there, and that's when I submit. That's your answer. Okay, let's look at the last one. X squared to the 1/6. Okay, this one actually is easier than those two. So there's no funny business in here. You got x squared to the 1/6. If you got an exponent raised to another level, you multiply them. So it's x 2 times 1/6. Punch that in on your calculator. And your calculator should spit out x to the 1/3, because it'll simplify it for you. Okay, now morph that to a radical. The x goes here, the 1 goes here, the 3 goes there. So easy cheesy. Okay, these next 3, they're given in radical form, and you need to morph them to exponential form. So here we go. Okay, I've got the 5th root of 7x cubed. That is the same thing as this. I got 3 of them. So that's the 5th root of 7x times the 5th root of 7x times the 5th root of 7x. I got 3 of them. And that is really, since they're all the same index, they're all 5th roots, you can times this to this to this. So that's the same thing as the 5th root of 7 cubed x cubed. Because 7 times 7 times 7 is 7 cubed. Now, if I morph this to its exponential form, that is, if I do one at a time, so that's 7 to the 3/5 times x to the 3/5, and that's fine. Or it's 7x to the 3/5, either one. Okay, the middle one is a little different. Okay, the middle one, that 2 is only the exponent of x. The exponent of 5, if there's not one, it's understood to be 1. So I'm going to kind of do these each on their own, each of these factors. So it's 5 times x squared. So here we go. I'm going to do the 5, and that's going to be 5 to the 1/4 times, everything's times. If I do the x, it's going to be x to the 2/4. And my next move, we got to simplify. I'm going to simplify this 2/4. So 5 to the 1/4 times x to the 1/2. And that is it. Okay, last one. Your last one's even a little more different. Okay, last one. Your index, if there's not one, it's understood to be square root, so it's 2. And let's see. Okay, so 15 is out on its own. And I'm going to go x to the 3/2. Okay, that's one way. You either did that, and I guess that'll be okay, or you simplified your radical first. So you kind of have an improper fraction here. 3/2 is really like 3/2 equals 1 and 1/2. So if you had 1 and 1/2, that would be 15 times x to the 1 times x to the 1/2. So 1 and 1/2 is really 3/2, and this probably would be considered to be maybe more simplified. So you can get that way by simplifying this first. So it's a square root, and you've got a cube in here. So I'm going to rearrange this cube into a square and 1 left over. And this square root is going to undo that square, which means x comes out. So with the 15, I got an x, and then I've got 1 left over. And that is the same thing as 15x times x to the 1/2.